Hi, everybody. In this video, we're going to start section 2.3, which focuses specifically on linear functions. So we're still talking about functions here, but we're talking in this section about linear and also going to talk more about slope. So a lot of the topics here you're probably familiar with, but we're going to, again, bring in that function notation here as well. So just a quick introduction here with an application. And the point of linear functions really for all mathematics is to help us model the real world and to figure out what's going on around us. And there are a lot of applications that are linear in nature. And this is just one example. So this is a graph that compares literacy and child mortality. So on the x-axis, you're looking at the percentage of adult females who are literate. And then on the y-axis, you're looking at under 5 mortality per 1,000. And we see an overall trend here as more adult females are literate, then that child mortality rate for those under 5 is decreasing. So there seems to be some sort of relationship between having adult females who are literate and a decrease in child mortality. Now, the dots here are all the actual real data points. So this would be actual real data points throughout the years, for instance. And this set of points is called a scatter plot. Now, when we draw the line that passes through them or near the points, the line that best fits the data in a scatter plot is called a regression line. So we're not going to do too much in this particular lecture with scatter plots and regression lines, but again, it's a really common application here that you see often in algebra courses or in statistics courses as well. So our goal is to always try to find that line that models that real world data. So we'll do a little bit in this, this chapter, but again, you can see it also a lot in other algebra courses and statistics in particular. And you want to keep in mind too that we want to find the line that best fits the data. So it's obviously not going to be a perfect fit. There are plenty of data points that are not on this exact line, but you can see that it does fit the data pretty well overall. It kind of runs right through the middle of that data. So your regression line sometimes is also called the line of best fit. So you hear that word, those words best fit often. Okay. Now, this is kind of the point of your linear functions, again, to model that real world data, but let's go back a little bit and go through some of those basic definitions. So one thing we talk about a lot with linear functions, of course, is the slope. So the slope of a line measures the steepness and also the direction of the line mathematically. So it looks at the ratio of vertical change, which is the rise, to horizontal change, which is the run of a line. And here's just an image from your text that I copied into the lecture notes. So again, you have the idea of slope here, and you can think of slope in different ways. You can think of it as just the change in y compared to the change in x. Now, change in y runs along the vertical axis, so that's why it also is the same thing as the rise or the vertical change. And your change in x, now x runs along the horizontal axis, so that's why it's the same as the idea of run or horizontal change. If you have two specific points, you can actually find this mathematically as well by subtracting the y values in the numerator and the x values in the denominator. So you're looking at this change from one point to another point, and again, you're comparing that ratio. How much does it change vertically to how much does it change horizontally? All right. Now, when you have two sets of points like this, the easiest way to find your slope is to use that formula on the page before. So with 2 points, you want to use that formula, y2 minus y1 over x2 minus x1. That's the easiest way to find the slope when you have 2 points. If you have a graph, you can also count a little bit easier. Or if you have an application, then maybe you can find the vertical and horizontal change. Maybe they're just given to you in the problem. But for 2 points, this is sort of the best way to go about it. It doesn't matter which point you call point 1 and point 2, so you can pick whatever you want. The key thing is more so that you start with the same point when you subtract on both the numerator and denominator. So if I'm going to start with this point as my y2 for my numerator, then I'm going to start with the same point for x2 in my denominator. You want to be really careful. The formula has a minus sign in the middle. So when you subtract here, I'm doing 4 minus, and then my y1 value is -1. Here I have a -2 to start, minus my x1 value is -3. So just watch out for all those negatives. I'm going to simplify here. My two negatives will cancel, so it's just 4 plus 1. And then same thing, my two negatives here will cancel, so it's just +3. And I'm left with 5 over 1, which is just 5. So my first slope here is 5. For the second one, we'll do the same thing. So my y2 is -2 here, and I'm subtracting that with the y1, which is 4. My x2 is 2, and I'm subtracting that with the x1, which is -3. -2 minus 4 is -6. Here, those two are going to cancel out, so that actually becomes just 2 plus 3. So it's -6 over 5. So our m here is -6/5. Now, notice that one of our slopes is positive, one of our slopes is negative. So actually, the positives and negatives do affect the direction of the line. So there's 4 possible things that can happen. So first of all, you can have a positive slope. So let's say your slope is positive. When that happens, your line is going to be some sort of increasing line. Now, it may not look exactly like this. It could be a little flatter, a little steeper, but it's going to be increasing when you have a positive slope. When your slope is negative, like in our second example here, your line is always going to be decreasing. Now, the third thing that can happen, which we haven't seen yet, is a slope of 0, right? In between the positives or negatives, you obviously have 0. So a slope of 0 actually gives you a perfectly horizontal line. And there's one other thing that can happen. Your m could also be undefined. And undefined occurs when you have a vertical line. Now, when you have a 0 slope or undefined slope, let's talk about those for a second. So for a 0 slope, what's going to happen is you can still use these formulas here, and you'll get that 0 in the numerator. So maybe you have 0 divided by 2 or something like that. So the answer is just going to be 0. So it works out perfectly fine. Also think about the graph, right? If our negative slopes are decreasing lines and our positive slopes are increasing lines, well, it would make sense that a slope of 0 is perfectly flat, right? It's not going to be going up. It's not going to be going down. It's going to be perfectly flat. So for undefined slopes, what ends up happening here, you can still use the formulas, but you're going to find that you end up dividing by 0 in the formula. So we don't always use this formula, but if you do use this formula, you would end up having that 0 on the denominator. So that would be undefined. That's how you could tell that way. Another way to think of it too is if you look at a perfectly vertical line, it's sort of confusing in the sense that, well, is it increasing? Is it decreasing? It's perfectly straight up and down. So it doesn't really make sense to talk about it having a concrete value. It's almost like it's going towards like infinity or something like that. So we don't talk about slope being infinity. We say that it is undefined. So something that's a vertical line would be undefined there. One other thing I do want to note as well, and I'll just kind of make a little note over here, is that the larger the absolute value of the slope, the steeper the line. So let me just switch that over a little bit. Perfect. And then the closer to 0 the slope is, the flatter the line. Okay. So not only does slope tell us the direction, is it increasing, is it decreasing, is it flat, is it undefined, but it actually also tells us how steep everything is as well. So if you have a larger absolute value for your slope, you're going to have a steeper line. So for instance, a slope of 5 here is bigger than the absolute value of -6/5, right? So this is going to be a steeper line. It's going to be more vertical. This value is closer to 0, right? This value is a little bit over -1, I guess a little bit under -1. -1 is much closer to 0 than 5 is. So this will be a flatter line compared to this one. So not only does it tell you the direction, if it's going up or down, but it also tells you how steep it is. So those larger absolute values, the more positive you get or the more negative you get, the steeper those lines are going to be. Whereas slopes that are closer to 0 are going to be much more flat. Not quite horizontal, but they'll be looking more horizontal compared to some of your other slopes.